Hello, this is Jared Niemi with a mini lecture on finding p-values and critical values for constructing confidence intervals. Alright, this lecture is going to be focused on finding p-values for symmetric distributions such as standard normals and t-distributions. Recall the definition for a p-value is the probability of observing a test statistic as or more extreme than that observed if the null hypothesis is true. And three key aspects of this definition that I want to point out is that you first calculate a test statistic from your data. So you take all of your data and boil it down into one number called the test statistic. You need to know the sampling distribution for this test statistic under the null hypothesis. In this talk, that's going to either be a standard normal or a t-distribution. And you need to find this region that is as or more extreme than what you observed, as or more extreme than your test statistic. And I just want to point out that the difference between one-sided and two-sided hypotheses is simply this region, right? So the test statistic remains the same and the sampling distribution under the null remains the same, but the region that's more extreme changes depending on your hypothesis. All right, so we're going to be assuming for this slide that we have z-statistics, but we could easily be talking about t-statistics or t-scores as well. But so right now, let's assume that we have a test statistic z, and that's lowercase z, and that test statistic has a standard normal sampling distribution if the null hypothesis is true. A standard normal sampling distribution is a normal distribution with mean 0 and variance 1. We can have one of three types of hypotheses. We can have a two-sided hypothesis, or a one-sided hypothesis going in one direction, or a one-sided hypothesis going in the other direction. Notice the difference here. Nothing has changed. We still have the same quantity for test statistic, we still have the same sampling distribution, but depending on our hypothesis leads to three different regions that are as or more extreme. We're going to now rewrite these regions to have a bit of a consistency when we're trying to find the p-values. So we're going to rewrite the two-sided hypothesis to be the sum of the two tails. So this is the tail where the standard normal is greater than some value, and here's the tail where the standard normal is less than some other value. All right, so now we can see why it's sort of two-sided, because there's two pieces of information we need to hold on to. But because the z and t are symmetric, and we'll talk about this in the next slide, we can rewrite this sum as 2 times this probability right here. All right, we can also rewrite this probability right here as that. Right, so the probability that z is greater than little z and the probability that z is less than the negative little z are the same. So both of these have to do with the fact that the distributions are symmetric, and we'll show that on the next slide. All right, but the key feature here is that we've now changed all of these p-value calculations into the same type of calculation. So in every case, we have the probability that capital Z, or the standard normal, is less than some value. Right, z is less than, and what's changed is what it's less than. So here it's the negative absolute value of the test statistic, here it's the negative test statistic, and here's the test statistic itself. All right, and the reason that that's convenient is because this function, as a function of little z, or now I've written it as c, is called the cumulative distribution function for the standard normal. All right, and we're going to be using software packages that can calculate that cumulative distribution function in a little bit. Okay, but first let's make sure we understand this symmetric distributions. So both the standard normal and the t-distribution are symmetric around 0. So here's a picture of what they look like. Right, you see this sort of bell-shaped curve. And the key piece here is that the areas under this curve, remember that the area under the curve determines which values are likely. So values around 0 are likely, and values away from 0 are not very likely. And the key piece is because this probability density function is symmetric around 0, the blue area and the red area are equal. So said with probabilities, the probability that z is greater than c, okay, that's the blue area, is equal to the probability that z is less than negative c, that's the red area. Right, so this is the key piece about symmetric distributions that allows us to make those probability calculations a bit easier. All right, so let's give an example using the paired t-test that we've talked about previously. In that example, we have a one-sided hypothesis, namely that the difference is greater than 0. We have a test statistic that has a value of 2.43, and this test statistic under the null hypothesis has a t-distribution with 7 degrees of freedom sampling distribution. So what we're interested in is calculating this probability that a t-distribution with 7 degrees of freedom is greater than 2.43. On the previous slide, we saw that we could write this as the probability that t is less than negative 2.43. An alternative way that we could write it is using properties of probability. So we could write it as the probability, this probability on the left side is equal to 1 minus the probability that t is less than 2.43. You might be wondering where the equal sign is on one of these two sides. It turns out because t is a continuous random variable, the probability that t is exactly equal to 2.43 is 0. Okay, so let's use some software to do these calculations. Here's the example in SAS using proc-IML and the cumulative distribution function for a t-distribution with 7 degrees of freedom and the cutoff value of 2.43. Equivalently in R, we again use the CDF of a t-distribution with 7 degrees of freedom. And in both these cases, we obtain the p-value of 0.0227. Alright, so there's a related quantity called the critical value that's used in constructing confidence intervals. Here's an example from the the difference between two populations mean example. And here what we're interested in is finding what should this t cutoff be. And here we're borrowing the notation from the textbook The Statistical Sleuth, where what this really means is we want to find this value right here, such that the area to the left of it is 1 minus alpha over 2, which means that the red area up here has area alpha over 2. Right, so if we rewrite this as C is equal to this cutoff right here that we're interested in, then what we find is we need to find the value C such that a probability of a t-distributed random variable with df degrees of freedom such that that probability is 1 minus alpha over 2. And again, remember that this 1 minus alpha over 2 is the area, the white area. So this looks exactly like the types of things we were calculating before, but before, for the p-values, we knew C, and we wanted to know what the probability was. Now we know the probability because we're going to set alpha, but we need to know what C is given that value of alpha. So here's an example in SAS and R. If we set alpha equal to 0.05, which is a very common value for alpha, then 1 minus alpha over 2 is 0.975. Again, we can use proc-IML now with the quantile function for a t-distribution with 7 degrees of freedom and find out what the cutoff is such that the probability is 0.975. Alternatively, in R, we can use the quantile function for a t-distribution with 7 degrees of freedom and find what the probability is. Alright, so this 1 minus should not be here. Apologize for that. Once we've gotten rid of that, then both R and SAS will agree, and we'll find a t cutoff of 2.364.